this is lesson 21, activation energy. So we know that temperature usually causes a reaction to speed up. For example, if you put a glow stick in hot water as opposed to cold water, if you're making bread, you usually put your dough on top of the oven in order to rise because it helps the yeast to react faster. And the collision model tells us that molecules must collide in order to react. Well, that seems easy enough, right? In order for two reactants to react and combine into products, they must hit each other. So if we increase the number of collisions, we'll get a faster reaction. And we know that if we increase the temperature or increase their concentration, we're going to increase the collisions. So our reaction rate should increase. Remember, if we increase the temperature, we increase their speed, and if they're moving faster, they're going to hit more often. So again, remember that only a tiny fraction of collisions results in a reaction, because not only do they have to have the correct amount of energy, but, yep, you got it, the correct geometry is also a requirement. So here again, let's talk about the geometry, which we often call the orientation factor. In order for a reaction to occur, molecules have to hit in the correct orientation. Okay, so here, this is a reaction, chlorine, which is green, and NaCl, and I have color-coded the elements for you to make NO plus Cl2. Well, in order for this to happen, the Cl has to hit the Cl to make Cl2, and the Cl here must break away from the NO. So here we have a green chlorine hitting the green chlorine of the NoCl, and that will make a successful collision. However, if the chlorine hits the red nitrogen, now we can't form that bond, and so they'll just bounce away. That will not react. Remember, the activation energy is the minimum energy in order to react, and it comes from the kinetic energy of the molecules. And that activation energy is used to stretch, bend, or break bonds in order to reform them. So the lower the activation energy, the faster the reaction. The transition state, remember, is that unstable arrangement when the reactants are about to form products if they have reached the activation energy. So for example here, this H3C and C, in this reaction the N and the C just flip and change places. So the transition state would be halfway through the flip as this is turning. Now, how do we find the activation energy? Or how do we find K knowing the activation energy? We have an equation called the Arrhenius equation, which is K, the rate constant, equals A, which is a constant, we call that the frequency factor, times e to the negative activation energy over RT, and R is the gas constant. So, as activation energy increases, the reaction rate is going to decrease. So how do we find the activation energy? The first thing we can do is we can graph the natural log of K, which will give us a graph where Y is natural log of K, M is the negative activation energy over R, X is 1 over T, and Y is ln of A. So if we graph the natural log of K versus 1 over T, our slope will be negative activation energy over R. Mathematically, in these should be moved over, we can find the activation energy because the natural log of K1 over K2 will be equal to the activation energy over R of 1 over T2 minus 1 over T1. So, K and temperature. The rate of reaction changes with temperature because, remember, K changes with temperature. And K also depends on activation energy. So, again, this equation can be used to show how K changes with temperature. And notice here, R is equal to 8.31 joules per Kelvin's moles. So the Arrhenius constant A takes into account the frequency of successful collisions, and it has the same units as K. So, why is Arrhenius important? Again, it allows us to find the activation energy for a reaction.